Hello everyone, my name is Mohsen. I'm a PhD student at Purdue University, and today I'll be presenting MoneyMorph, a censorship-resistant rendezvous using permissionless cryptocurrencies. This is a joint work with Pedro Moreno Sanchez and my advisor Aniket Kate. Censorship is an ongoing problem in today's world, and it is an important one because censors are restricting the free use of internet to the users in their regions. This is a well-studied problem over the past few years, and to circumvent the censors, many circumvention tools have been introduced over the years. Some examples are Tor, VPNs, decoy routing, and so on. Let's take a look at the problem in more details. On the left, we have the censored region that is being monitored by the censor, and on the right, we have the uncensored region. The problem that Alice faces inside the censored region is that it wants to connect to a website outside of the region that is banned by the censor, meaning that any connection to and from this website is going to be blocked. A possibility is to connect to another node, which in our example is a Tor bridge, and then the bridge connects to the website on behalf of Alice. But the question is that how would Alice connect to this bridge? Currently, one way to get this information, which we call the bootstrapping information, is through email. Alice sends an email to the Tor project and she will receive the information such as the IP, port, and the public key of the bridge. Now, having this bootstrapping information, Alice can connect to the bridge and from the bridge to the destination website. The connection to the bridge by Alice is possible because the censor does not get this information about the bridge, which otherwise would be blocked as well. The problem with this approach is that it lacks formal definitions and analysis. For instance, we do not have a definition of a bootstrapping scheme, nor its security privacy notions such as the security against the chosen cover text attack. In this work, we aim to address these shortcomings by defining the bootstrapping scheme and the privacy security notions of interest. So what we propose in this work is to introduce blockchains as a new rendezvous for retrieving this bootstrapping information. In this scenario, we have another entity called the decoder that sits in the uncensored region and helps the censored users in obtaining the bootstrapping information. I like to emphasize that we are not claiming that this approach should be used over all other options out there. We are proposing a new medium for users that can be used orthogonal to all other approaches. In this scenario, the rendezvous for requesting and retrieving the bootstrapping information is the blockchain of the cryptocurrencies. In the first step, the censor user sends a challenge transaction to the public blockchain, which contains a challenge message that can only be decoded by the decoder. In the second step, the decoder scans the transactions in the blocks and decodes them to see if there is a message intended for it. Next, it will send the corresponding response to the challenge message as an encoded transaction to the blockchain. In step 4, the user can look for the specific transaction and decode the transaction and obtain the response message. Finally, using this bootstrapping information, it can connect to the bridge and from the bridge to the website. So why are cryptocurrencies a good medium for transferring bootstrapping information? Over the past few years, we have seen the adoption of blockchains and cryptocurrencies in many of the censored regions. Here are just a few news headlines that show the presence of cryptocurrencies in such countries. Furthermore, cryptocurrencies utilize many cryptographic operations, which many random variables and public keys are used, that we can benefit from to encode ciphertext and keys. Now that we have seen the overview of the goal of this work, let me tell you in a bit more detail what are the contributions in this paper. First, we define the Stego bootstrapping scheme with its security and privacy properties. Next, we introduce MoneyMorph, our instantiation of the Stego bootstrapping scheme for Bitcoin, Ethereum, Zcash, and Monero. Finally, we show the feasibility of MoneyMorph by implementing it in the test network of the mentioned cryptocurrencies. In the rest of the talk, I plan to overview each of these contributions. Let's start with the Stego bootstrapping scheme itself. But before that, let's look into the threat model of the censor, which we adapted from all the prior work in the censorship domain. We consider a malicious adversary with network capabilities in the censored region. However, it has no control over the decoder or its network. Further, the adversary can prevent access to the rendezvous, but doing so will have a negative economic impact. The reason being many digital assets are currently being transferred to and from the censored regions. Finally, we consider that the adversary can act as a normal user to also obtain bootstrapping information. The Stego bootstrapping scheme can be seen as a two-way handshake. A challenge from the censored user to the decoder in the forward direction, and the corresponding response from the decoder to the censored user in the backward direction. The two-way handshake can be considered as two independent one-way handshakes that include an encoding and decoding algorithm. This approach, however, requires the decoder and censored user knowing each other's public keys in advance. In practice, instead, the censored user knows the public key of the decoder, but the decoder does not know the public key of the censored user. This state of the affairs is what motivated us to define the Stego bootstrapping scheme as a unique two-way handshake where only the decoder's public key is required. In fact, let me give you a little more details on how our scheme is defined. The scheme consists of four algorithms. First one is the encoding scheme in the forward direction. In the first step, the censored user Alice uses the decoder's public key, which is known to everyone, to encode the challenge message that incorporates a tag tau along with her own public key. We can think of this as a key encapsulation mechanism where Alice encapsulates her public key for the decoder to later use to reply to her. Now, having the challenge cover text, Alice sends it to the rendezvous. In the second scheme, which is the decoding in the forward direction, the decoder first retrieves the challenge cover text from the rendezvous. And using its private secret key, it decodes the challenge cover text and reveals the challenge message, the identifying tag, and Alice's public key. Similar encoding and decoding process is done in the backward direction, where the encoding is initiated by the decoder by using Alice's public key to encode the response message. After encoding, the decoder obtains the response cover text. And finally, it will send the cover text to the rendezvous. In the final decoding scheme, Alice retrieves the response cover text from the rendezvous, and using its private key, it reveals the response message, which is the desired bootstrapping information. Now we move on to the security and privacy goals of the Stego bootstrapping scheme. First is the rareness, meaning that decoding a regular transaction, which is not a cover text, does not yield a valid challenge or a response message. The second goal is security against chosen cover text. We say that the Stego bootstrapping scheme is secure against chosen cover text attacks if the adversary, given a cover text, cannot tell whether it encodes a message of his choice. Now that we have defined the Stego bootstrapping scheme, let's move on to introducing MoneyMorph. MoneyMorph is our instantiation of the Stego bootstrapping scheme. MoneyMorph is constructed of two main blocks. One is the cryptographic operations that are performed locally and is independent of the cryptocurrencies. And second is the encoding scheme based on the cryptocurrencies. Let's begin with the crypto operations performed by Alice. First, using its own private key and the decoder's public key and performing the Diffie-Hellman key exchange, Alice generates a shared master key. We note that this key exchange is non-interactive, and before receiving the challenge cover text, the decoder does not even know that Alice has performed this key exchange. Then, using the hash-based key derivation function, three other keys are derived. One symmetric key for encrypting and decrypting the challenge message, one for encrypting and decrypting the response message, and a final key that serves as the public key of a cryptocurrency address, which we will see it in action later. The reason we have two different keys for the challenge and response messages is that the length of the corresponding messages can differ, as we use plain symmetric encryption based on one-time pad. Next, we have the encryption of the challenge message to generate the challenge cover text, and the decryption of the response cover text to retrieve the response message. The same set of operations is also performed by the decoder, with the difference that the public key of Alice is unknown to it. What decoder does is that it first extracts Alice's public key from the challenge cover text and then performs the Diffie-Hellman key exchange. the key derivation procedure remains to be the same. However, the decoder decrypts the challenge cover text that was encrypted by Alice, and to respond to Alice's request, it encrypts the response message to create the response cover text. Next, we have the encoding scheme of the cryptocurrencies. For each cryptocurrency, we have a unique encoding scheme tailored for its characteristics. We have instantiated our encoding scheme on 4 different currencies: Bitcoin, the most popular cryptocurrency today; Ethereum, that focuses on complex smart contracts; Monero and Zcash, which are privacy-preserving currencies. We begin by giving an overview of the format of the Bitcoin address and transactions. A Bitcoin address is made of a pair of verification and signing ECDSA keys. Bitcoins are exchanged between addresses by means of a transaction, and in the simplest form, a transaction transfers a certain amount of coins from one or many input addresses to one or many output addresses. Here we are seeing an example of a transaction that has one input that holds 2 Bitcoins, and there are 2 outputs where after the finality of the transaction, they will hold 1.5 and half of a Bitcoin each. The Bitcoin protocol uses a scripting system that specifies how coins can be transferred between addresses in a transaction. In particular, coins are locked in an address according to a script public key, a script excerpt that encodes the conditions to unlock the coins. To fulfill such conditions, we use another script called script sig. The figure is showing where each of these scripts are placed. For this transaction to be fulfilled, we need the sign script of the input in the signature section. But what are these scripts? The script is composed of a combination of opcodes that can be used to fulfill a particular task. In general, there are 5 main types of scripts being used in Bitcoin today, which are listed here. In order to reach the goal of hiding our bootstrapping information among the transactions of other users, we have to pick a script type that is used the most. By observing all the transactions in the Bitcoin blockchain since its inception, we see that pay-to-public key hash is the most used output. Here we show its public key and the signature script. The places that are highlighted with green are the variables that are taken from users, and the rest are fixed opcodes, which they fulfill an intended task of transferring coins to an address. We further analyze the transactions and observe that 70% of the transactions have only one input and 80% of the transactions have 2 outputs. Therefore, the transactions that we use in Bitcoin are going to have 1 input, 2 outputs, and where the script is type of pay-to-public key hash. Here we are showing the challenge transaction that is sent by the censored user. I'm going to skip the details and give an overview of the encoded data, which is highlighted by blue. Here our focus is on the outputs of the transaction. The first output encodes the challenge cover text instead of a public key hash, which means that the coins locked in this output will not be spendable anymore and will be lost. The cover text is an encryption of the challenge message, which in this example, it is requesting bootstrapping information for a OBFS3 Tor bridge. And the second output encodes the public key of the address that the decoder will use to respond. This key is the aforementioned key that was derived from the master key in the crypto block. Finally, we have the public key of the user incorporated in the signature of the transaction that the decoder will extract to perform the Diffie-Hellman key exchange. Similarly, here we are showing the response transaction with 1 input and 2 outputs. The decoder splits the response cover text and encodes them into 2 outputs as we saw earlier. In this example, the response cover text is the encryption of the IP, port, and key of the requested Tor bridge. For the sake of time, we are going to skip the encoding for Ethereum, Zcash, and Monero and refer you to our paper for the details of their encodings. In the following, we will show the summary of our findings for these 4 cryptocurrencies. But before that, we will go over the system goals which we use as the criteria to select a certain transaction type within each cryptocurrency, such as the pay-to-public key hash in the previous slides. The first one is the percentage or number of transactions that have the same type and structure with the one that contains the encoded message. We want this number to be as high as possible in order to make the task of the adversary difficult in blocking or detecting the message. For each of the cryptocurrencies, we select a transaction type that is most used in that blockchain. Next, we have the cost efficiency. As we know, there is always a cost associated with the cryptocurrency transactions, so we aim to reduce the cost for the honest censored users. Keep in mind that the request for bootstrapping information occurs infrequently, and these costs will be amortized over time. Finally, we want to maximize the bandwidth or the number of bytes that we can transmit through the Rendezvous. The table is showing a summary of our findings. We see that Monero has the highest percentage of sibling transactions with 42%. The next highest with 32% is Bitcoin, and arguably the most used currency worldwide. Among the four, Zcash, which is a privacy-preserving currency that hides the amount and recipient of the transaction, provides the most bandwidth, followed by Monero. The reason that these privacy-preserving currencies provide more bandwidth is because of their inherent usage of more random variables and public keys that can be reused to encode the random-looking cover text. The cheapest fees for the currencies goes to Zcash, which requires less than 1 cent for its transaction fees. The runner-up is Monero with about 3 cents, and the most expensive currency is Bitcoin with about 50 to 70 cents in each direction, taking into account the transaction fees and the amount of coins that will be lost. So in summary, we see a trade-off between the different goals, and users can choose whichever cryptocurrency based on their priorities. Now we move on to the implementation of MoneyMorph. Once again, we divide the cryptographic operations from the transaction encodings. For the cryptographic operations, we prototyped our implementation in Python using a Core i7 16GB RAM laptop, and observed that creating a fresh pair of keys takes about 120 milliseconds on average. Furthermore, driving the shared key and the 3 symmetric keys took about 41 milliseconds on average. And finally, both the encryption and decryption of the messages took less than 1 millisecond. In conclusion, we see that even the current commodity machines have more than enough processing capabilities to serve the censored users in multiple cryptocurrencies at the same time. Next, we move on to the transaction encodings. We implemented the encoding scheme for Bitcoin, Zcash, and Ethereum. As an example, we took Tor OBFS3 as the message with 8 zeros as the tag. The hexadecimal of the challenge message, encryption key, and challenge cipher are shown. Note that the challenge cipher is a simple XOR of the challenge message and the encryption key. But what is important here is the challenge cipher that needs to be encoded in the transaction. As an example, here we are showing a real Bitcoin transaction that is in the Bitcoin testnet. As we see, the challenge cipher is encoded in the second output of this transaction. Here we see another example for the Ethereum, where the same cover text is split into 4 parts and is encoded inside the input values of a well-known smart contract. I conclude the talk with the main takeaways. First, we defined the Stego bootstrapping scheme with the security and privacy properties, which were the rareness and the security against the chosen cover text attack. Next, we introduced MoneyMorph, our instantiation of the Stego bootstrapping scheme for Bitcoin, Ethereum, Zcash, and Monero, and further compared them based on percentage of sibling transactions, their cost, and the amount of bandwidth they provide. Finally, we showed the feasibility of MoneyMorph by implementing it in the test networks of the mentioned cryptocurrencies. Thank you for watching and listening to this talk. You can always contact us through email and Twitter. The link to the paper and our implementation of MoneyMorph is also provided below. If there are any questions, we will be happy to answer them. Thank you.